Hello, you are listening to Pankaj Rai, and in this video we will be discussing the numericals of the chapter Magnetic Effect of Electric Current. And in this we will be studying the moving coil galvanometer. So let us begin. Now consider that we are having a magnetic field over here, and let's say the magnetic induction of magnetic field is B. Moving ahead, let's say that we are having a conductor over here, okay, and let's say we are passing a current through it. So let's say the length of conductor is L, and let's say the current which is passing through it is I. Okay, I'm not showing the circuit for current to pass. Just assume that there is a conductor and current is passing through it. So when we are having a conductor in a magnetic field, it will experience the force, and the direction of the force would be given by the Fleming's rule. Now it will the force which it will experience is given by the equation, which is F is equal to BIL. So this is the force which this conductor would experience. Okay, it would be magnetic induction, electric current, and the length of the conductor. So that would be the force. Now let's say instead of a conductor, I am having a coil over here. So let me have a, let's say, rectangular coil. So here we are having a rectangular coil, and let's say the breadth of the coil is B, the length of the coil is L, and let's say the current is passing through it. Okay, now look at the two arms, which is the left one and the right one. Okay, now both are of length L, so both will experience the same amount of force, which will be BIL, but the direction of the force would be opposite to each other. If you follow the Fleming's rule, so this conductor would experience a force outward, and this conductor would experience a force inward. Okay, but they will be equal in magnitude, they both will be BIL, and these two conductors, which are breadthwise, okay, they are parallel to the magnetic field, so they won't be experiencing any force. So now this is a rectangular coil, and out of which the two arms are not experiencing any force, and the two arms are experiencing force which are opposite in direction and equal in magnitude. So it will create torque, and the value of the torque is given by it is given as magnitude of one of the force, either this one or this one, as both are same, multiply by distance between the two forces. As we can see here, the force in either of the arms is BIL, and the distance between two forces, so that is the distance between these two arms, and that is nothing but the breadth of the coil, so that will be B. Okay, now I can also write it as that torque is equals to BI times LB. Now LB is length times breadth, which is the area of the coil, so I can say that torque is equals to BIA. Okay, now this is for a single coil. Okay, now let's say there is a coil having two number of rotations. Okay, so it would be 2 times of this. Let's say there is a coil of having n number of turns, so the torque will be n times BIA. So that is the formula for the torque, and this torque is called as the deflecting torque. Now when this torque will get applied on this coil, so this coil will start turning. Okay, now let's say that this is the let's say, yeah, this is the axis of the coil through which it is rotating. Okay, let's say it will be rotating in this direction. Okay, now this coil in mcg, if you will read the construction of the mcg, it is attached with a wire, and that wire, let's say this wire, will start twisting. Okay, and when this wire will twist, it will try to twist back or bring back the coil to its original position by providing a restoring torque, and that restoring torque is directly proportional to the angle of deflection. Okay, the amount of angle by which the coil is rotating would be directly proportional to the restoring torque. Okay, and that restoring torque can be written as c theta, where c is the twist constant, and that depends on the material. Okay, in mcg the wire is made up of phosphor bronze, so that twist constant will depend on that material. Okay, now what I said is, when the current will pass through this coil which is kept in a magnetic field, it will start experiencing force in these two arms, and the coil will start rotating, or this the coil will start rotating, and as the coil will start rotating, the phosphor bronze wire will start getting twisted, and as and when it will start getting twisted, it will try to twist back, and it will apply a restoring force, restoring torque, and that restoring torque is will be directly proportional to the deflection. If there will be more deflection, the restoring torque would be more. If there is less deflection, the restoring torque will be less. For equilibrium, I can say that the deflecting torque would be equal to the restoring torque. This is too obvious, so I can substitute that N times BIA is equal to C theta, and from this I can say that I is equal to C upon NBA times theta. Now why I have put this in bracket? Because these four terms are constant for a given mcg. Because if a mcg is given, then the phosphor bronze wire or any metallic wire would be fixed, so the twist constant would be fixed. N is the number of turns in the coil, that would be fixed at the time of manufacturing. B is the magnetic induction, that depends on the magnets which are kept inside the mcg during manufacturing. And A is the area of the coil. The area of the coil, which will be length times breadth, would also be fixed during manufacturing. So these four terms would be constant for a given mcg. So I can say that I is directly proportional to theta. That means if I pass more current through the mcg, there will be more deflection. If I pass less current through the mcg, there will be less deflection. So this is the simplest theory of moving coil galvanometer. Okay, now to solve the numericals, you should be aware of the terms and their units. Okay, so let me mention them. So let us begin with F. So F we know is force, and the unit is newtons. Moving ahead with B. So B we are aware of, it is magnetic induction, and magnetic induction is given by Weber per meter square, or it is also given by Tesla. I, you are aware of it, this is electric current, and the unit is ampere. Moving ahead with length and breadth, so L is the length and the unit will be meter. B is the breadth of the coil and unit will again be meter, and A would be the area of the coil, that will be given by length times breadth, so it will be meter square. Now after that we are having N. So N is a number of turns in the coil, and that is a pure number, so it is unitless. And after N we are having torque. So torque, you can see here, the torque is force times the distance between them, so it is Newton meter, that is the unit of the torque, Newton meter. Moving ahead with theta, theta is the angle of deflection through which the mcg rotates, and that angle of deflection is having a unit of degree. Moving ahead with the last one, which is c. Now c is the twist constant, and the unit of twist constant can be derived from yeah, look at this. We are having that torque is equal to c times theta, so c is equals to torque by theta. Now torque is Newton meter by theta, so it will be Newton meter per degree. So that is the unit of twist constant, which is Newton meter per degree. Now, if you remember all these terms with their units and these formulae and what are the meaning of different terms, you can solve any numerical on this topic. And for your practice, I can tell you that you can try out the solved examples 4 and 5 from your textbook, and problem for practice number 1. These questions are based on the topic which we have just discussed. Thank you very much.